Good morning to all. Today I want to share my opinion for a simple foundation system in floodplain alluvial soil, more especially encountered at the north bank of Brahmaputra Valley. Before going to start my topic, I want to show the map of Brahmaputra Valley. This is the Brahmaputra Valley, this is North Bank, and this is the South Bank. It is Brahmaputra Valley started from Pasighat and in South Bank at Purokhuram Kunda up to Bay of up to Bangladesh border, that is Dhubri. And this is the river Brahmaputra. It is starting from Tibet and entering Arunachal Pradesh, thereafter flowing through Assam, then entered Bengal and Bangladesh, finally met at the Bay of Bengal in Bangladesh. This is the mighty river Brahmaputra, which is the longest river of India and third longest river of Asia. In terms of discharge, it is the biggest river of India. Innumerable tributaries at the both bank, all are coming from hills, especially from Tibetan hills, then Arunachal hills, then Bhutan hills, and in South Bank, Nagaland, Manipur, all the hills, this tributary is coming and make Brahmaputra is major river in India. The foundation soil of floodplain alluvial deposit in north bank of Brahmaputra Valley chiefly consisted of three types of soil. Number one, the top mantle of soil varying a thickness of 0.5 to 1 meter below the ground level, chiefly constituted of silty sand, which we can classify as SM and SC, or both symbol, dual symbol we can use. This deposition region is lower velocity, very low velocity. This, this floodplain deposit was deposited by the very low velocity. The silt particles are macroscopically appears like very fine and it behaves like silty clay, which normally we can say SC type of soil. This top mantle has a great benefit to the people of Brahmaputra Valley because it is highly, this type of soil is highly fertile, and best suited for agricultural use. Shallow water level also helpful for agricultural production. Just below the topsoil, as I explained, the zero point 0.5 meter to 1 meter, a poorly graded fine to medium grain sand, which we can classify as SP, of variable thickness, generally entire Brahmaputra Valley, more or less North Bank and South Bank, but South Bank soil is little different since it is coming from nearest hills. The amount of coarse grained sand increasing with depth and occasional sub-rounded to rounded pea gravels are also noticed. Another type is very dense and compact vulgated gravelly sand SW was normally encountered at a depth of 25 meter to 30 meter below the ground level. However, this north bank of Brahmaputra Valley started from uh, Pasighat to Dhubri. Everywhere, it is not same. The thickness of this layer varies from place to place. As for example, near the foothills of Arunachal Pradesh and Bhutan, some difference are noticed. In this area near foothills, a very dense gravel cobble boulder bed was encountered at a shallow depth, even some places 5 to 6 meter below ground level. This type of cobble boulders are also encountered at a shallow depth in most cases of the river bed too, like river Jarasar, river Jiabhoroli, river Dhansiri, all this river Subansiri, all this river in river bed itself it is encountered. The average permeability coefficient of this sundry stratum, which normally we say SP stratum has been calculated 1 cm per second using Allen Hazen theory, which is 100 d10 square, d10 in centimeter. It was calculated average 1 cm per second. In addition to this high permeability, the subsoil water level is very close to the ground level. This is a major hurdle of of foundation at construction of foundation at a little higher depth. Very high hydraulic heads more or less always noticed because as I told earlier, when we excavate a pit, water level will be encountered, normal water level will be encountered, it will be say about zero point 0.5 meter or zero point 0.7 meter or 1 meter even. When we are when we are excavating up to 3 meter, we shall be pumping out to go beyond 1 meter. We shall be pumping out So the hydraulic head will be outer level and inner level difference is 2 meter. 2 ton per square meter hydraulic pressure will be acting at the foundation trans bottom. So this shall lift it up all the soil particles because individual soil particles weight of these soil particles will be around 1.5 to 1.67 like that. So this particle shall be lifted up. If its head is 1 meter, if hydraulic head, this is difference of water level is 1 meter, then there shall be no upliftment of fine materials. Since it is more than 1, it will be automatically all the fine particles shall be lifted up. I have personally visited many problematic work sites from Pasighat to Dhubri. I had seen everywhere the same problem. More specifically, for construction of tall structures like water towers, those are average reservoir they are constructing, microwave towers. I have I had been fortunate to associate some microwave towers at the North Bank as well as some hilly state of Ansi Hills where height varies from 100 meter to 150 meters. So in such cases, we are facing great problem. Transform, uh, Transmission towers, etc., where the overturning force is governing factor, which generally require little deeper foundation mainly to resist the overturning forces by soil surcharge. In some microwave towers, the dead load of the structure is 30 ton and overturning forces is that is horizontal thrust is 300 ton. So definitely to balance this we have to adopt the soil surcharge. We must consider for soil surcharge, otherwise it will be very highly costly since we cannot go for huge concrete underground. These are the site conditions of various sites. I have these are my old files. This is you see, it became almost slurry. It became almost slurry. This side you see, this side, these are almost slurry. Besides that, this automatically when the soil have zero shearing resistance at the bottom, weight of upper soil has not resisted by the soil strength at the base. So automatically there will be slides or soil slips okay, which we can normally instability of the cut slope. Here the same problem but they have provided some steel shuttering so side is not slide cut slope is stable but inside both horizontal and vertical permeability affected this foundation soil, transforming this soil to totally quick state, which we can say liquefaction. we can say it liquefaction. Liquefaction normally when seismic vibration is happen during pore water come out and soil particles will be coming up almost in liquid state where shear strength is zero. Here shear strength is at the bottom, shear strength is zero, and the existing height of this above base level to top level it is about 3 meter. So it is instead of since there is no water, total weight will be say about uh, 2 ton per cubic meter bulk density. Since soil moisture is there, so automatically it is sliding down. This is all this. These are slides. These are slides. In this context, I had think why we are not capable of giving a good solution for all general application at North Bank. Yes, if we try, we can. So I had gone through a detailed study to find out the some simple means for less time consuming and economically efficient too. First, I must say about the merit and favorable quantities of this type of soil formation and secondly the anticipated worst effect during and after construction because this is a peculiar soil. So subsoil water level is very close. Soil is permeability. There is no amount of cohesion. That is in skeleton interlocking system is no bindings in there. If there is some amount of binders, then the adhesive force will be there. So it will be as a whole, it will collapse, not uh, particles after particles. So we are thinking this, we find out the average angle of internal friction of the up to the significant depth, which is normally 1.5 to 2b, in no case be less than 30 degree. Angle of repose, this type of soil, and never be less than 30 degree. Since the foundation soil has a tendency of increasing shear strength with depth, I have conducted many investigations in North Bank for many high structures, low structures, breeze, and lot of investigation I have conducted. Nowhere I find angle of repose less than 30 degrees. Somewhere we are getting little more. However, since sleep angle of soil of any kind, whether it is hard clay or plastic clay, although the alpha equal to 45 plus minus 5 by 2, yet all scientists and scholars they are confirming that the shear angle is 30 degree. So since at the below foundation the shear angle that is lost, this low distribution angle is 30°, so automatically the upper shear failure shall also be 30°. So under no case it shall be angle of the force shall be less than 30°. Further, the North Bank soil, North Bank sandy soil, which were normally encountered below 1 meter, extending up to say 30 meter or 25 meter like that, that soil has a tendency of increasing shear strength with depth. This is the basic reason soil is pervious. It has a permeability of average 1 cm per second, 1 centimeter per second. So, due to self weight of the soil, that is surface effect, soil is gradually oozing out the soil water inside the void shall be decreasing and soil shall be naturally compacted due to self weight only. Void ratio is decreasing proportionately to depth. This is entirely based on my earlier innumerable geotechnical investigation works and case studies, and sand is totally free from long-term time consolidation settlement because water is incompressible material. So, in case of clay, permeability has a relationship with settlement. More the pervious, settlement time is very less the settlement time. Less the permeability, settlement time is very high because from a clay soil, impervious soil, where it is 10 to the power -7 or -9, no water can come out from the pores, where permeability is 1 centimeter per second. That soil pore water can easily drain out at a loading, slight overloading, it will be coming out. So in sandy soil, there shall be no long-term time consolidation. In our IS code also, we are not required to calculate the settlement of sandy soil. We know the settlement of sandy soil shall be completed during construction itself. More applied load will be more when foundation is completed, some amount of settlement is over, and when substructure will be completed, then some amount of settlement will be over. Before 100% load, this settlement shall be completed. So this type of settlement is immediate and elastic settlement. Elastic settlement little bit different. Immediate settlement is application of load, settlement will be completed. Elastic means due to elasticity of the soil, there will be some amount of settlement which soon after release of load soil shall regain original state. So another sand has a tendency of natural compaction and consolidation under saturated condition and as such elastic and immediate settlement, if there be any, shall be completed during the nominal loading soon after completion of foundation shelf that I already discussed. The pore water shall ooze out due to high permeability of soil formation very rapidly. The major problem, these are merits. Now we are discussing about the demerits. The major problem is excavation below water level. Generally, in this type of soil, fine to medium grain SP soils, the foundation soil normally worst affected due to hydrostatic pressure, mainly by soil permeability. More especially in combination of both vertical and horizontal soil permeability. Sometimes slopes became collapse, which we can say landslide, landslip, whatever it may be, side may collapse because at the bottom of the side slope there will be no shear strength of soil. Another thing is particles movement along with water with seepage line or from uh, vertical permeability, it will be uh, very prominent and it may so happen the soil formation sometimes transform to quick state. The fine particles are mostly coming out with water flow and finally the soil has developed flowing tendency. Here two photographs were there, but these two photographs where it missing I do not know. This may be those two photographs. This is you see this is soil slides, soil slope sleep, and here it is this foundation soil transformed to quick state. That means this soil has it in this point this best is resting before coming out this water. Water coming out means water carrying also some fine particles like silt and fine grained sand. Develop finally behaves like floating particles having no strength, which is not good at all for construction of foundation. The foundation shall settle down. Nowadays, this phenomenon is becoming much common due to popular use of mechanical excavator because there is a difference between mechanical excavation and manual excavation. In earlier days, manually excavated. When manually excavated, it gives in manual excavation it gives total separation time of soil particles. Another is the less amount of soil has been removed what amount of water is coming out that can be pumped out easily. In mechanical excavation, even we go for in hard clay formation, thixotropic loss of strength for about 200 to 300 was noticed. In earlier, one of my sharing videos, I have discussed about there are few chisel type nail in front of the cutting bucket which enter to the soil first, then little amount of cutting with cutting tools, and entire soil will be mechanically take out. It does not give much time to shear the soil formation with the mother part and excavated part. So automatically entire soil will be disturbed. Under the problematic situation, foundation cannot be provided. In this type of situation, no one can take responsibility of putting the foundation in that type of state. Whatever it may be, this type of soil and this type of soil. I am here, I am standing here. My shoe already inside the mud. That is a completely loose formation. I am standing here observing this point and this point. These are whatsoever it may be, these are very simple economic. Uh, in earlier days, deep type of problems were taken care of by providing a thin layer of cobble, boulders, gravel to arrest soil particles movement with water. Sometimes bamboo matting, mostly in Bangladesh, was also used. All these are local common practice. We can use a term as layman concept. Whatsoever, these are very simple, economic, and best effective means to transform some loose soil to hard base. Because these soil particles are lighter than the hydraulic pressure due to difference of 2 meter or 3 meter, whatever it may be. But if we go for some heavy materials, then soil particles cannot coming with the soil. In this in this diagram you see the same condition here, like this same condition. It is providing 200 to 250 or 350, what may be ever, gravel, cobble, boulders. No sand is required to mix with here because sand will be coming up automatically. Water will be coming up. We shall be draining out using some pump sheet at corners, and after laying this gravel, boulders, more bigger the size of the gravels, cobbles, and boulders, it is best working. because it cannot be moved up by water. And after above that, there is a polyester sheet. A polyester sheet is provided so that water cannot go up, it should be going this side. Water should be going this side. Outside there is a place, beyond the foundation there is a place where from where we can take out the water. This is boulder, gravel boulder filling to make it little hard. Little hard. This successfully used many places in my supervision itself, many places in Bangaigaon and a lot of places I have used this technique. This is, you see, this is alternative. This is, these are the mature bamboo. They are in Bangladesh. Bamboos are cheaper, but boulders are costlier. So they cannot go for boulders. They generally prefer to use bamboo matting. Since they are putting all this bamboo like a mat, one close to other, like this, and they will be putting one polyester sheet so that water cannot come coming upward. It must go this side, and all this void will be filled with sand. Upper portion of this bamboo shall be filled with soil, sand, and the lower portion shall be filled up naturally. Those sands are coming with water. Since 19, 1960, this type of practice normally used before introducing the geobag or geofabric or this modern technological development. Before introduction of this modern technology, this simple method were used since history, since long history back. During 12th century, 12th to 13th, 14th century, uh, the kings of Ahom, they have used some rock floors. Rock floor means a rock piece, rectangular piece of rock at some loose soil. This was their original concept. Nowadays, scientists have been developed many advanced technology to avert this type of critical foundation problems. These are lowering of water level, jet grouting, cement grouting, bentonite grouting, peripheral sheet piling, and many more. Lowering of water level is a very costly proposition. Jet grouting is also a very costly proposition. Cement grouting is also a costly proposition. Bentonite grouting is costly proposition. Peripheral sheet piling only effective if there is some impervious layer below the sandstone, either impervious, clay soil, or hard rock. Then only sheet pile shall work properly. Otherwise, we can lateral protection we can provide by sheet piling, but vertical permeability we cannot prevent. Undoubtedly, these are highly efficient and effective. Notwithstanding, these matter no one can afford for day-to-day projects works because of high cost, time factor, and expertise agency. I beg apology to all of you. There are a lot of typing mistakes like that no one can afford, no one cannot afford. There are some lot of since uh, I am speaking and my typist he was typing. I beg apology for these unwanted mistakes. Lot of mistakes are there. Please bear with me. These are adopted only for prestigious projects and unavoidable circumstances only. Like this Z grouting and cement grouting, these methods were used in Naranarayan Setu, the bridge over river Brahmaputra at Jugigupa. It is Northeastern Railway construction project. In that bridge, the jet grouting and cement grouting was used. My study, as I told earlier, I decided to study. So my study includes minimize the depth of foundation for easy and trouble-free execution, efficiency of use of 30 bar as dual bar, cost efficiency, SBC analysis at shallow depth. My study based on some assumed soil parameters which are finally in lower range. These are average and below up to the significant depth considering 3 meter as foundation depth and width is 8 meter, then automatically significant depth will be coming 15 meter. Up to uh, 15 meter, my and below will be 15. Average submerged density, it shall be 1 ton per cubic meter. Average angle of repose 30 degree. Average angle of internal friction is 30 degree. And all required parameters such as BC, tension load of double bars have been estimated as per 11th BIS and IRC codes. These are never be these values what I adopt. It's an actual value of field expected to be little higher than these values. I am collected the lowest value from my innumerable other works and soil behaviors also. Because angle of repose 30 degree, phi shall be little higher. Phi shall be little higher. Because angle of repose equal to angle of friction in loosest condition. In loosest condition, angle of repose is equal to angle of friction. So, I am considering the soil is very loose. So, in worst condition, what shall be parameters I have adapted? The subsoil water level mostly at north bank of Brahmaputra Valley found in the range of 1 meter to 2 meter below ground level depending upon the ground elevation. In highland it is 2 meter, in lowland paddy field it is 1 meter. In some time in it may it may come to point half meter too. And as such, open cut excavation is considered trouble free maximum up to a depth of 2 meter. We are considering 1 meter, then we can go another meter because 2 meter minus 1 meter hydraulic head will be 1 ton per meter square. So our grain weight, if we can calculate the density of the single grains, it shall be more than a 1 ton per meter square. So that 1 meter sun particles cannot be lifted up by water. So I had checked SBC at a depth of 1.5 meter and 2 meter below ground level. Using these soil parameters stated above, the SBC at 1.5 meter below ground level has been estimated using earth pressure theory, the original theory of earth pressure, that is Rankine theory, which nowadays we use to cross-check the depth of foundation. Another method is 6403 using C5 method, another from N value as, as under for foundation base of 8 meter by 8 meter at the depth of foundation as 1.5 meter. And what I find in this case, in 1 meter, 1.5 meter, our lowest value, I am not considering the highest value, I am considering the lowest value. The lowest value is coming this 10.38. In seismic condition, it is net SBC, non-seismic net SBC, and it is seismic condition net SBC man. It is gross SBC. QAZ is gross SBC. That means 10.38 plus 1.5, the surcharge 1 ton per cubic meter. It is net gross SBC is this much, and seismic condition net is this much, and gross is this much. Considering the lowest value, we can efficiently provide the foundation at a depth of 1.5 meter, considering a net non-seismic SBC of 10.38 ton per meter square. To avoid the construction problems. In case of what combination of all forces, all load, we can efficiently increase SBC up to 14.47 ton per meter square. You see, in combination of all forces, that means tension, seismic, everything. In case of such condition, our we can go up to 14.47 ton per meter square since it is gross as we see under seismic condition. We can go up to this extent, but in normal cases we should not go beyond this limit, and in worst condition our permissible limit is 14.47. Accordingly, I have calculated the SBC at a depth of 2 meters using the same parameters and same equation. In this case, 11.54 ton per meter square is minimum. So, in this case also, we can provide efficiently the foundation at a depth of 2 meters, adopting an SBC of 11.54 ton per meter square. In worst cases, we can go up to 16.42 meter square. Because you see, in big foundation base, our developing length is much higher. Our all the bars has some sufficient bigger diameter. So we need some developing length also. For that, uh, in no case it shall be exceeded 16.42. So we can efficiently provide. However, considering the excessive height of the tower, exceed tension loads, excessive tension load, we can easily provide shallow foundation at 1.5 meter to 2 meter with a provision of boulder masonry cover over the foundation considering 2 ton against the soil size of 1 ton, 2 ton cubic meter against which shall be more suitable for structure and windfall in cost economy. You see, normally our overturning forces are resisted by the soil weight of this soil weight. From here it will be 30 degree slope. This soil will be give surcharge effect against the uplift moment of foundation. Overturning forces uplift this when there will be a much higher load, then this side will be going up and this side shall be going down. This shall not be more than SBC, which we can go up to 16, up to 6, um, up to 16 ton. As I said, 16.42 ton. We cannot exceed 16.42, and when it will be, there will be no compression load. It should be not less than 0. This is our basic requirement. To resist this uplift thrust due to overturning, instead of soil surcharge will be when our foundation need is base of 3 meter to get the proper soil surcharge. We are providing 2 meter, that we are having a shortfall of 1 meter. That is 1 ton per square meter. We are replaced for 1 ton. We can use the boulder with some cement mortar Lean cement mortar, 1 in 6, 1 in 8, like that. 1 cement, 6 sand. We can lean mortar we can use just to bone this. Outside there will be natural soil, and after completion of this foundation, there will be here also. If we provide the foundation for that at 1.5 meter, we need only 75.75 meter boulder filling. Boulder missionary works. It lean cement, that is one cement, sand, sand 6 to 8, just to keep bondage, little bondage. In case of 2 meter, we need only half meter of boulder pitching. Instead of fighting against all the worst situation at site, we can provide the foundation safely at 2 meter with a provision of half meter boulder cushion over the base. And in my opinion, it will be the best solution for all this type of problems. Alternatively, we can easily provide foundation at shallow foundation 1.5 to 2 meter below with provision of double bars of 30 mm up to a depth of 3 meter below foundation. A double bar 3 meter long 30 mm dia considered efficient for a tension load of 0.7 ton per 0.7 ton per bar. 0.7 ton per bar is not a matter of joke. We can provide it very efficiently at a closing space, say about zero point 0.7 meter or half meter like that. We can easily use. So, and it is not very less time consuming, since all the construction agencies, they are using Puckland or JCB. They are using JCB or Puckland. The bar can be penetrated down at a static pressure. I personally saw that 3 meter, 4 meter bars, uh, bamboo piles were installed within a day. A bigger foundation, it is about 9 meter by 9 meter, 8 meter by 8 meter, like that bamboo pile and sand piles. They are complete one foundation a day. So it is very effective. But dwell bars, it should be included in concrete foundation base. The dwell bar, top of the dwell bar should be included in the foundation base, RCC base, with nominal developing length. Instead of 40D, in my opinion, 20D will be sufficient. Less than 20D, 10D also sufficient, because it will the dual bar connection in this foundation, we shall be making it L. We shall making L section of say 10D, 30 at 300 mm. It is sufficient. So we can go for that type of foundation too. Many developed countries consider this method as economically viable both in time and structural safety. Further, scientists claim that the shear strength of soil increases up to 50% very rapidly. During driving all the bars, it will be rotating at their some uh, at their specified angle. It will be penetrating like a screw. Not it is hammering down. It is automatically due to hammer or some pressure, static or dynamic, whatever it may be. it will be behaving like a screw penetrating inside the soil. So it will automatically increase the shear strength up to 50%. In a word, we must try to provide shallow foundation 1 meter to 2 meter below ground level at the north bank of Brahmaputra Valley, since the subsoil water level is very close to the ground surface level, and underwater excavation in granular soil create undesirable situations like soil slips, soil loosening, soil boiling may even lead to quick state liquefaction, which reduces soil strength nearest to zero. Further, to avoid this type of exceptional and critical situation, necessary precautions like use of high discharge pump set, use of proper shuttering or formworks or scaffolding is essential to prevent the cut slope instability. In the case of mechanical excavation, a gravel cobble boulders layer of 200 minimum thick generally be provided for thixotropic gain of strength of soil. In my opinion, shallow foundation without underwater excavation with a provision of requisite boulder masonry works is best suited foundation system in north bank of Brahmaputra Valley. Soil formation which is less time consuming, easy execution, resources availability, and overall cost economy and structural safety. Please all be happy. Please all be healthy. Please all be blissful at all times. Please all be contented at all times. I am always available at jcgogoi@gmail.com.